From the day Galileo Galilei turned his homemade telescope towards the heavens, humankind has held a relentless fascination for Mars. Named after the Roman god of war, Mars is the fourth planet from the Sun and the second smallest in our solar system. Despite its bleak, rust-hued landscapes, the seemingly barren planet of Mars shares some striking similarities with Earth. Like our home planet, Mars has polar ice caps composed of water and carbon dioxide. It even experiences distinct seasons. Evidence of ancient riverbeds and the presence of minerals that only form in liquid water suggests that Mars was once a wet planet, potentially filled with lakes or even oceans similar to those on Earth. These remarkable similarities and others lead us to a logical question. Did Mars once harbor life? Let's pause for a moment to study two compelling photographs. The first image, seemingly nondescript at first glance with its patterns and reliefs, actually conceals an astonishing testament to life that thrived billions of years ago. In contrast, the second image introduces us to the Martian enigma, a puzzle wrapped in red dust and mystery. This photograph captures Martian geological formations whose uncanny resemblance to terrestrial stromatolites hints at a tantalizing possibility, the potential for life beyond the confines of our blue planet. The striking parallels between these two images naturally beg the question: could Mars, much like Earth, have once harbored life? Could we be looking at the remnants of a long-lost Martian biosphere, preserved in these intriguing geological formations? And could it be possible that these structures, depicted in two photos taken millions of miles apart, share a similar biological origin? Let's venture further into this intriguing possibility, embarking on a journey of discovery that spans two planets and billions of years. Our mystery starts in Gale Crater, a vast impact scar 154 kilometers in diameter located near the Martian equator. In August 2012, Curiosity rover mission sent by NASA landed there, and soon as a part of ongoing mission in Gale Crater to study the planet's geological history and assess its past habitability, the Curiosity rover has found rock formations that resemble stromatolites found here on Earth. But first, let's figure it out what stromatolites are. Let's look at how they formed here, on Earth. These remarkable formations are created by cyanobacteria, ancient microbes that carpet the surfaces of stones in shallow, often harsh aquatic environments. Stromatolites are known to be the oldest evidence of life on Earth, dating back at least 3.5 billion years. In fact, the world's oldest stromatolites are found in Greenland with an estimated age of 3.7 billion years. Now almost nearly extinct in marine environments, they only exist in a few locations worldwide, such as Shark Bay, Australia, known for its very extreme conditions due to high salinity, extreme temperatures, low nutrient levels. The cyanobacteria are tiny architects that construct these stromatolite towers layer by layer, adhering to sediments while going about their daily routine of photosynthesis. Their oxygen-rich byproduct helps trap mineral particles, which over time form a sticky, calcified layer. Calcium from the surrounding waters solidifies these particles, creating a limestone layer. As new cyanobacteria flourish above, the older layers beneath are cut off from sunlight and perish, adding another flaw to the living high-rise. Stromatolites first appeared in the fossil record around 3.5 billion years ago and were most common during Precambrian period. Cyanobacteria responsible for these structures dominated among early Earth life forms, resulting in a great diversity of such structures. The abundance and diversity of stromatolites began to decline around 1 billion years ago. This decline is thought to be due to the evolution of grazing organisms that fed on the microbial mats of cyanobacteria, disrupting their ability to form stromatolites. With the Cambrian explosion, the rapid diversification of multicellular life around 540 million years ago, stromatolites became even less common. As multicellular life evolved and diversified, more organisms grazed on the microbial mats or stirred up the sediment, both of which disrupted stromatolite formation. Stromatolites are incredibly important for understanding the history of life on Earth and potentially Mars. The cyanobacteria that often form stromatolites were among the first organisms to perform photosynthesis, a process that produces oxygen as a byproduct. Over billions of years, these organisms helped to oxygenate Earth's atmosphere, paving the way for the development of more complex, oxygen-breathing life forms. The presence of stromatolites is therefore closely tied to this significant shift in Earth's atmosphere, known as the Great Oxidation Event. In addition, modern stromatolites are often found in extreme environments, such as the hypersaline waters of Shark Bay in Australia. This can provide us with clues about how life might survive in extreme conditions on other planets. Imagine if these formations, intriguingly reminiscent of stromatolites, were proven to be just that, or at least, products of similar processes. Such a discovery would be monumental. It would serve as strong evidence that life, albeit microbial, may have once thrived on Mars. This suggests that there were past environments on Mars capable of nurturing photosynthetic life, the architects behind such structures. The implications of this would reach far and wide, impacting our understanding of astrobiology on a fundamental level. It would serve as groundbreaking evidence that life, in its myriad forms, is not unique to Earth. So, what clues hint at a biological origin for these curious, stromatolite-like structures found in the Gale crater on Mars? The key lies in the crater itself, more specifically, the historical presence of water. Stromatolites on Earth emerged in shallow, sunlit bodies of water. Numerous studies of the Gale crater suggest it was once awash with rivers and lakes. Observations by the Curiosity rover bolster this theory, indicating the presence of liquid water in the Martian past, a fundamental ingredient for life as we understand it. Peering into the Martian landscape of the Gale crater, scientists discern signs of liquid and ice that once sculpted the land. Features such as gullies and pathways, reminiscent of those formed by rain or melting snow on Earth, are clearly visible. Likely, these ancient waterways carried sediments, depositing them in lakes nestled within the crater. Consider a cycle spanning billions of years, lakes filling and drying out, only to be replenished again. Some scientists speculate that this process even could have continued until a few million years ago. Some even go as far as to suggest that Gale crater may harbor water today. How the water arrived there, however, remains a mystery. It could have fallen as rain on the Martian surface, could be the result of seasonally melting ice, or it might have even surged from underground aquifers. The clues are there, ready for us to uncover the history of water, and possibly life, on Mars. Let's explore another body of evidence mainly about structure and morphology of fascinating objects of the Gale crater. We've previously touched upon the remarkable visual similarities between Earth's formations and those found on Mars, but now let's delve deeper into the details. One of the defining characteristics of stromatolites, as we've seen on Earth, is their unique layered structure. These layers are typically formed by microscopic architects over extended periods, capturing and binding sedimentary grains within complex biofilms, almost like living masonry. Over time, these microorganisms create intricate layers of life and sediment that accumulate to form the mounds we recognize as stromatolites. The Martian structures discovered in Gale crater display a strikingly similar layered composition. This correlation extends beyond just layering. The structures on Mars also share morphological similarities to terrestrial stromatolites, specifically those found in Western Australia's Pilbara region. Consider their overall shape and dimensions. The Martian structures, like their earthly counterparts, display a rounded, dome-like form that suggests gradual, layered accumulation over vast stretches of time. Then, take into account their surrounding environment. The structures on Mars are associated with what appears to be an ancient lake environment, further echoing the environmental conditions in which stromatolites thrive on Earth. An illustrative comparison can be made between the Martian structures and the stromatolites in the 3.5 billion-year-old Dresser Formation in Pilbara. Both display finely laminated structures that coalesce to form larger, mound-like formations, resembling ancient biological high-rises. Additionally, both appear to be associated with ancient environments that cradled persistent or episodic bodies of water, underscoring the potential for past life. This collection of evidence, ranging from the physical form to the environmental context, paints a compelling picture. It's almost as if we're looking into a mirror, seeing the reflection of our own planet's biological history in the geological formations of Mars. But before we draw any conclusions, it's important to remember that all the evidence we currently possess is indirect and inconclusive. Whether the stromatolite-like structures on Mars have a biological or abiological origin remains to be proven. Mars, a planet we're still learning about, could host a variety of geological processes that mimic the structures we associate with life. Consider mineral precipitation, a process where mineral-laden water creates layered structures as the minerals precipitate out. Alternatively, sedimentary processes, which encompass cycles of sediment deposition and erosion caused by changing water levels, wind, or even seismic activity, could form structures resembling those created by life. Even volcanic activity can lead to the formation of layered structures through the deposition of ash. Interestingly, here on Earth, we have natural formations that, at first glance, seem too intricate to have been formed purely by geological processes. Take the Giant's Causeway in Northern Ireland, for instance. This extraordinary landscape, with its hexagonal pillars, was created around 60 million years ago, not by the hands of giants as legends would have us believe, but by volcanic activity. In order to determine whether these Martian structures are of biological or non-biological origin, we need further investigation and analysis. A detailed study of Martian rock samples returned to Earth could provide us with the answers we seek. We stand on the precipice of discovery, ready to unlock the secrets of another world. As we delve deeper into the mysteries of Mars, each finding brings us one step closer to answering the age-old question: are we alone in the universe?